Mentally math!
Let's get mental!
Alright.
You were really good at that.
That's alright.
5.
A for effort.
8.
Okay, I'll give you a minute to get out ahead of me. So I'm not spoon feeding this to you. Wow, I guess people in YouTube land are getting a nice detailed conversation from the kids in PE outside. Okay, I'm gonna take a couple more.
No estimation. Yeah, I guess so. You did?
But there was. I hope you wouldn't give the game away so that we could see who falls for it.
Even if I gave it away, I would still forget myself. That's what I do.
All right.
I messed up.
Okay, well that should give you time to get a couple ahead of me. You should already be like well into it.
No, I'm just asking.
Okay, so yeah, I'm getting started. Okay, so this one we have two negative values turns into a positive value. So this one is 0. No, happy. It's a happy 0.
Wait, that's not a 0. That's noble. Wait, that's like a pool.
Picky, needy people.
Now
Mhm.
yes, now he's sweaty.
Alright, and then last time I checked, 25 squared was 625. Whoops, then I'm painting that on there.
I'm not so sure actually.
Well, do it out then. Yes?
Do it out, Bob.
What? Well, check yourself by actually multiplying it on your paper and see what happens.
Isn't it supposed to be mental?
Yes, but if you get an answer that doesn't make sense, then check and see why. Alright, then we can add 10 to 32 to get 42 divided by 6 gets us 7. And then for this one, probably a couple different paths you could do to success, but I'm going to say, well, say 12, then carry my 1, then 9, and then multiply by 10. I'll put my unit in so I don't get minus 1 point. And so getting me to 94 and 2/10 centimeters. Then metric conversions. So for this one, there are 10 millimeters in a centimeter. So we're multiplying that by 10 to get 15 millimeters. Then looking at that, 30 divided by 5 multiplied by 6 gets us 36. And four-sided figure that only has one set of parallel lines. How about see how many people can tell me? Ready? 1, 2, 3. Trapezoid. Good.
Yeah.
Trapezoid. Trapezoid. Alright, then 12 times 12, 144 minus 4, 140, divided by 10, 14, plus 1, 15, times 2, 30, plus 3, 33, times, divided by 3, 11, times 5, 55, minus 1, 54, divided by 6, 9, and then the square root would be 3. Right next to our happy face. Okay, so today we're talking about algebraic terms, and unfortunately the term also has a different term in math for terms, so we're going to end up saying the word term over and over again until we are utterly confused. No, just kidding. Okay, so a term in general is just a word that people use, essentially. Let's see. I was looking up some dictionary things, but a word that denotes an object, or anyway, we use the word term all the time. And then in math, a term is essentially part of an equation. Is a term. So a term is really anything that can be part of an equation. So, and some of the terms that we're using in this class, we could have exponents with variables, just regular numbers, all that goes under terms. I think something like pi is also a term. So really, it's just kind of an umbrella for anything that you put in an equation. And then, being a little bit more specific, types of terms can be numbers or variables. And, so say all of these are terms. And then you could also say variables. So essentially, you could say a variable with an exponent, or just a plain old variable, something like that. Then collections of terms are called polynomials, or collection of terms that make an equation. And so if there's one term, we call that a monomial. Well, mono means one. Like if I'm only playing one speaker, I'm playing mono instead of stereo. Then binomial, and think nomial, number, nomial. So polynomial, something that has multiple numbers. And then so binomial, like bicycle, like has two wheels. So binomial has two numbers. Yes?
Monorails have only one rail.
There we go. That's maybe a better example than the speaker example. Yes, a monorail. Yes, but we don't call a regular train a biorail though. Yes.
So could this keep going to quadnomials?
That makes sense. If you told me that, I would believe you. The book only goes up to trinomials. And so trinomial, tricycle, so that has three numbers. Nomial number, try 3. So that's kind of our vocabulary for this. And then beyond that, what the lesson is about is using the commutative property, which means you can rearrange numbers in addition or multiplication, and your answer will still come out the same. So we do this thing called collecting them. You could think of it also as combining them. You could also think in some cases of canceling each other out. I like combining because, if you're combining a positive and a negative value, that still, that can mean canceling, or it can mean adding. So say for this one, for starters, you can think, how can we rearrange this equation, this formula, so that it just kind of makes more sense and it's easier to see what might combine or cancel each other out. Oh, look at all this. Yeah.
3x plus x plus y minus y.
Yeah. So 3x plus x plus y minus y. And one thing that can be helpful, a couple things that can be helpful when we're thinking of these is, remember that if we have a variable and there's nothing in front of it, that still means there's an imaginary one, right? So we can think that each of these has an imaginary one in front of it for figuring out how to combine these terms. And you could also, sorry, my one here is just bugging me here. There, you're a better one now. Say we could also put some parentheses to give us a little help on how to combine them. So once we've got that, what can we do to make this a more simple problem? Yeah.
We could do 1y minus 1y, which equals 0y.
Mm-hmm.
So
basically.
Plus 0.
Yeah. So basically, it would be
That's
3x plus 1x, which equals 4x.
Good. Excellent.
Excellent.
Yeah, I totally did that on purpose. Yes. Totally, because I'm really clever like that. Yeah. So yeah, 4x can be our very simplified version of this equation. Yeah.
If the side on the left would be 4 and the side on the right is 0, then it would be 4 times 0. Wait, no, never mind.
We're not multiplying these.
No, I thought I didn't see the plus sign. Never mind.
Okay.
Yep.
Okay. Well, my writing's a little not great.
I didn't see correctly.
Okay, it's all right. Don't worry about it. Okay, so here's one that's just a little bit more complicated. Now, keep in mind that, and I'll let you try to figure this out ahead of me. Keep in mind that variables with exponents are in a completely different category than ones without exponents. So you cannot combine these guys and these guys. So I'm going to give you a minute to figure this out first.
What's your question?
Uh-huh.
So for these problems, would you put like parentheses or anything?
That's really up to you if that helps you organize the information. What you end up with should not need any parentheses.
But it is allowed.
Well, I mean, as far as figuring out your path to the correct answer goes, anything that helps you organize your information is certainly allowed. Sure. Okay, so just to do spoilers, the first thing I'm going to end up doing is rearranging these so that the like terms are next to each other, and maybe do some parentheses, and then I'm gonna sort it out from there. So I would suggest you do the same thing. Okay, so I'll assume this has given people time to get started. I'll go slowly. Okay. Now, and one thing that I am seeing in the format that's being presented to us, that needs to go. Are you using it for anything right now, or are you playing with it? Then put it away, or it's a toy, and I'll deal with it like you're playing with a toy. So the variables with exponents go first. If you did it in a different order, I believe you would still be mathematically correct, but you would be not doing it in the format that we're kind of being shown to do it in. Okay. And then after that, it's variables. Move the signs around? Oh, well, say this. I'm putting a plus. Very good question. I may have should have pointed it out. I'm putting a plus sign in front of this because this is it's a positive value. So there is an imaginary plus sign in front of it. And so once I move it over here, for sake of clarity, I can put my plus sign in front of it. Does that make sense? Okay. And then my numbers. Okay. And then still. Oh, I was going to. I mean, though, honestly, you don't have to. You really don't. Yeah, that's just the thing. If it helps you to organize it, sure, put in parentheses. But you don't have to. Well, I think what matters here is what you end up with. So, I mean, you could just look at that and just write down your final answer immediately. Right? I'm just doing it step by step so it's obvious what we're doing. But you could easily just look at that and go, oh, hey, yeah, there's the 2 times x squared, and there's a x squared over there, so I could just put down a 3x squared, and I mean, you could do all this mentally. Sure, but I'm just trying to go slowly step by step so that it's obvious what I'm doing. Okay, so looking at this, I've got my 3x squared, because remember there is an imaginary 1 there. And then plus, and then once again, my imaginary 1. So 3x minus 1x is 2x. Well, you don't know what x is, so you don't have enough information to do anything with the x with the exponent, right? I mean, if we knew what x was, then we could move forward with it. But as it is, this is as simplified as we can make it. And then 4 minus 1 will get us a value of 3. And there we are. Ta-da! Oh, what? Are you wondering, can this and this be combined?
No. I'm just... Okay, never mind. Okay, I'm good.
Okay, yeah?
Can't that make 5x squared?
No, because you cannot combine an exponent x with a regular x. Because these are being added together, not multiplied. Now, if these were being multiplied, and that's gonna be there's gonna be another lesson where we're combining these things where there's multiplication involved, and that's where we're actually gonna have to like break this down way far. It's gonna be awesome. You'll love it. But there's a lot more to it if it's involving that. But yes, if we were multiplying these, then you could do that. But we're adding them, and so they're kind of their own different terms, and you can't combine them. Okay, so yeah. Right. So that's what I was saying, is you would not be mathematically incorrect if you put it in a different order than this and this and this. Because of the commutative property, it would equal the same thing. But as far as I can see how it's presented in the math programs, it always is put in this order. So I'm assuming that's kind of a format that we're supposed to follow. That's my assumption, and that's how I'm gonna do it. But it wouldn't change your answer, and I suppose if you put it on a test in a different order for me, I'd probably look at it and go, well, equals the same thing. They combine the terms. I don't think they ever said it had to be in that order, so probably give credit on it.
It's just getting better and better. Like once you add the x, then you add the x and the exponent.
Yeah, it does seem to be putting it into that order every time for a reason, so I think we should do that. Okay, how are we? 1, 2, or 3?
3.
Okay, how are we feeling?
Okay,
2.5. That's fine.
Basically
Okay,
fine.
I had thought about doing this, but I think we're good to stop, right?
Yeah, we're
Okay, just one thing to note over here is they did throw the whole thing they threw pi in here, right? But
Can we eat the numbers?
oh no, we don't need to. But say this one, you could take your. It's the same thing, right? Is you take your positive 3 pi and your negative 1 pi to get 2 pi, and then you'd combine these two, and these are two positive values. So that would be like that. Does that make sense?
Yeah.
Okay, great. All right.
Bye.